just north of Austin, Texas. The camera is directed to a pivot polishing setup for an American clock wheel. This is an old American clock wheel that was built. The clock was built around the turn of the century. This is a lantern pinion. This is the pivot polishing bed, and the pivot in an open center. To give an idea of what we have here, this bed, the breadth of this bed right here is 1/8 of an inch. And looking on the little TV monitor that I have here, which is about 12 inches diagonal across the picture, the magnification is about 7.5 times. So this is what this situation would look like with a moderately strong eye loop. The bed is constructed by drilling a piece of 1/8 inch diameter brass, and then a portion of the brass is cut away for this to form this flat surface. And in the cutting away, the diameter of the pivot hole is about 40% cut into the pivot hole, so that this is trapped in place. Though there is some slack there, we can see we can shake it, but we cannot lift the pivot from the bed. And we would polish the pivot by going on to this with pivot file, burnisher, stone, whatnot, in a polishing technique. In this tape, we will look into the classic American clock movement and look at some pivot conditions and how to correct the problems. And we will see this pivot polisher in work, in operation, and we will inspect the circumstances of the movement, showing where and how that this should be done to bring the movement back into good order. As we take a look here, we see the entirety of the wheel. We're driving the wheel with this crank pin that is slipped through the window of the wheel, and let's take a little better look to the driving head. Here we're looking at the headstock of the lathe, the collet, a driving disc that supports the crank pin. The crank pin is generally called a carrier. The names are not too clearly defined in technical literature on this, so if the names I use are not familiar to you, well, see if you can pick them up and use them for this tape. And the arbor, and this is between centers. We're running on this pivot, and we're sitting in, and let's cut the power, we're sitting in a female center here. This center is placed in the lathe collet, touched slightly with a handheld graver which trues the center. We're running on the pivot itself. I'm out of the picture. We're running on the pivot itself over here, and this gives us the highest degree of accuracy that can be obtained by any ordinary form of workmanship. It has all the advantages of the accuracy and the simplicity of the English turns, yet it has the flexibility and ease of use of the American lathe. This is removed from the lathe by withdrawing the tailstock center, and we lift the wheel out. And if we need to measure, inspect, whatnot, then we can slip this back in place and we lose none of the accuracy of our setup, and we're ready to go again. The the speed at which this is driven can be rather high. I usually drive this up close to 2,000 RPM. We're about 1,800 RPM at this point, and we would place a droplet of oil on this as we're carrying out the polishing operation. Now let's imagine that we want to polish the opposite end, and we would go on here like that. Our driving pin does not reach the window of the wheel, and this distance is not really feasible to do so. We could move this over like this if we could reach the wheel, but in this circumstance, let's take a different approach. We use a device here that in the machine tool industry would be called a driving dog. I don't know what this is called in the clockmaking, watchmaking trade. These pins are commonly called carrier. This is also called carriers in some literature. It's called drivers in others, but it's simply a little collar with a thumb screw, and we place that collar on the arbor and tighten the thumb screw like that. I'm having a little trouble getting in here because the lens of this camera is just over 3 inches from right here. The distance is about 3 inches, and I have to work to the side and view this in the monitor. Now the driving pin, notice here, the driving pin catches the driver here. We call this the carrier, this the driver. This would be a faceplate. The disc would be a faceplate in the machine tool industry. We catch like this, and here we go. Now we can work the pivot here. Notice that there is essentially no peripheral runout in this wheel, just a mite of peripheral runout, but there is a fair amount of runout in flat. We see this wheel wobbling when it's running. Let's come down to the lower speed, and you can get a better look at the driver and the carrier as it's carrying this wheel. Now, of course, to remove this, it's like that. If we wanted to swap ends, we could do this. We will need to remove our driver there. All right, let's look a little leftward and see what this looks like on the headstock end. This removes like that, and the crank pin can be changed in angle. It can be slipped out. This is a ring in place taper on the end of the pin. Sets up like that, and like this. Looking a little further, we see the headstock of the lathe, the pulleys, and come around and look in the tailstock area. We have the pivot beds, which are removable. We can see this pivot bed here. This slips in place. The set of tools has some 3 or 4 dozen of sizes of these beds. And if we loosen the collet, this is a collet holding tailstock. This is a collet in the tailstock of the lathe, and this is the adapter device. This is held in place by the collet, and then slip the bed in. So that's how the setup looks at that point on the lathe. Now let's look at the tool holder, or what would be the tool holder ordinarily in the lathe. This is a tip-over tool holder, but rather than a T-rest, this is a roller rest. This is a ball-bearing, very precision, very hard roller rest, and that is used to support the polishing tools. Note here, this is a pivot file. This is a very, very fine file. The texture of it is hardly detectable with the fingernail, and it is well worn. It is about as close as you can get to a burnisher and still be called a file. It's ground on the edges, and these are safe edges, also called a pillar file, and the corner is very, very sharp. So this says that we can go against the shoulder of the pivot in a filing operation like this, riding on the roller, and we can keep this pivot parallel because the roller here sets the flatness of the file while we're working. We would normally hold this down in the central region like this. We would rough the wear from the pivot with this tool, then use a burnisher or jasper stone or whatever to finish the pivot down to its ultimate finish. We set aside the lathe, and we'll take a look at the pivot working tools. This block of tools has about 110 individual, 120 I believe, individual pieces. If we look along the top here, we find there's 7 sizes of ball-faced punches. These are used for pivot hole work. Here is about 5 flat-face punches that's used for installing bushings. In the section here, we have a driver that we can use in the headstock in a collet, a female center, and a driving pin, and that is an adaptation for a different lathe setup doing a similar type of work. I use that in another lathe. This is a driver that I use in the Unimat lathe. This has a female center in each end, 2 sizes. This is the driver here, the carrier, with a little set screw that puts that in position. The piece that we looked at in the tailstock of the lathe is this receives the pivot beds like that. The pivot bed is inserted in here, and the pivot rested in this during the polishing operation. If the lathe does not have a collet holding tailstock, we insert the pivot bed in this device. Looks similar to the one previous, except that the end of it fits the taper in the more commonly found watchmaker's lathe. So we can use this in a collet holding tailstock or the more conventional tailstock. Here is the female pivot that we saw in the lathe earlier in the tape, the driving disc, and its pin or carrier. We have a variety of these carriers that we can use, such as various lengths of straight devices, curved devices like this, etc. These devices here and here are double-ended female centers to accommodate various sizes of wheels. We have some male centers here, and we also, these are male centers here. These three are oil sink forming swedging punches. Looking over the block, there is about 3 or 4 dozen of these beds in graduated sizes. Down in this end, we have female centers, graduated sizes of female centers. Now, in the polishing operation, should we have a radius right here at the shoulder that needs to be cut away, we would catch this in the female center on the right end, and with a handheld graver we would go right in and cut this radius out. So this this group of tools has more function than simply polishing the pivot. As pivots become larger and the stress is on the tool greater, we use this type of pivot bed. This is much larger, much heavier than the earlier ones that we looked at. This is for larger clocks. Beginning about here and on down to this end, we have the taper that fits the tailstock of the conventional watchmaker's lathe. In this region here, we have a cylindrical shank that we can catch in the collet holding tailstock, as we saw a few minutes ago on the tape. Down in this region are the driving dogs, or drivers, if you will. This is a series of collars, and these collars slip onto the shaft with a little long knurled thumb screw here, and that's used to get the driving force into the wheel. These are in graduated sizes. I believe there are 12 sizes here, and when the sizes exceed the largest one here, we use the more conventional driver of this type here, and I have several sizes of these. So this is what the pivot working tools look like. In the watchmaker's lathe, if we're doing clockwork, let's look in this block of collets here. This is number 40. This is number 65. The number 65 collet is the one that holds the tailstock adapter to support the pivot beds. The number 40 is the collet that we were holding this piece in. Those are in the lathe now. But this is what collet group looks like in watchmaker's lathe for clockwork. This begins with 31, runs through number 70. Smaller smaller clocks use much smaller collets, which I have in another block. The movement under study has been disassembled. It was terribly gummy and dirty. It's been rinsed off. We will make the repairs and then ultimately clean and put it back into service. Let's look at the plate. Let's look at the plates of the movement. See what we have. This is a front escapement movement. The verge mounts on this pin, the escape wheel here. This is the strike side, this is the time side. This says Sessions Clock Company, USA, Forestville, Connecticut. If we look into the back side of the plates, we find that there are no oil sinks on the holes. These holes are simply drilled and the wheels inserted in that. We don't find any evidence of any hole closing activity in time past. Looking in the front, the finish around several of these pivots look much like bushings, about 2, 3, 4, 5, about 6 of these. And presumably this was done from a decorative standpoint, because in reality the two plates began as identical pieces, and there was no treatment, no oil sink situation, no chamfering of the holes, whatnot on the back side. So it seems a bit capricious to do it on one side only. But as we look at this, we find that there is some serious wear in the pivot holes in these, and we'll see what we can do about these things. Let's take, for instance, in the time section, right here. Let's look at this wheel and see how much wear we have. I can stand this pivot in the hole, go round and round and round like this, and though this looks like a pretty large amount of wear, that is probably within limits of being usable. We pick up the next wheels that are in use, and this is the next wheel in the train, and we find the wear appears to be a little bit greater. And we try the next one. Look at this. See the angle that I can tip that pivot? Let's look at it on this axis. The distance that I can tip on that axis is different from this axis. That says that the hole is elongated. Pivot hole is elongated. Let's look at the escape wheel. Right here, the escape wheel, I can tip that pivot, tip that arbor this much. Now let's try this. Now it will tip this much. And let's turn it on this axis and see what happens. Look at this. That pivot hole is elongated almost a full pivot diameter. The length of that hole is, you could almost insert 2 pivots of this size into that hole at the same time. Now, the first place that I was tipping this, I'm holding the pivot underneath here. I'm holding it at the limit of the wear. And we see that the side shake in it is essentially 0. I can tip a little bit here, but the side shake is essentially 0 in the limit of the wear. If I pull up to the original position, then I could tip this angle. But if I turn so that I am tipping the arbor in the direction of the elongation, note this, that's approaching, that's about 40 degrees that I can carry that off of perpendicular. This is badly worn. Let's look into the front plate. Now, when we look on this, we would expect the pivot adjacent to the pinion to wear more than the other end, simply because that's where the greatest stress is. We have considerable wear. Here. The stress is also great there because the escape wheel is against this pivot. And let's try the next. We have to turn this over to insert this one. That's pretty much within usable limits. And we try this one, and that one needs some help. Now, those are the conditions that we have here. What we need is help in this elongated pivot. We need to be tightened up somewhat in some of these other holes, and we need some help in this pivot here. Now, I would judge that the thing we should do is place a bushing in this hole, and in this hole, and in this hole. This is pretty much a foregone conclusion. Now, let's examine this. I slip this pivot in the hole and carry it to the wear limit, and I have trouble pulling it out. I can slip it in the original position of the hole, in and out easy. But in the wear limit of the elongation, I have trouble pulling the pivot out. As it comes out, I can feel a grating feeling. If we turn this pivot on edge and pull our fingernail over it, like this, we find that it has what is called ringing. Ringing. That doesn't mean ring like a bell. It means that they're scored rings scored around the pivot. The inside of this pivot hole has the conjugate form of those rings, and what that says is that all infloat in this shaft ceases, and we're operating as if this pivot had 0 in shake. We have worn into this depression, and we have determined that it has essentially 0 side shake. And that is the power robber and the problems that we have to correct in the repair of this movement. Let's feel of this one. We said that we would bush this hole. That one has ringing in it also. And we'll try the pivot in this end, and there's no evidence of ringing in that one. Notice that the force is against this pivot, and very little on that one. This would be difficult to place a bushing in because we don't have access to both sides of the hole. It's possible to place the bushing in there, to ream that out and place the bushing in that hole, but it would be far, far easier to remove this bridge to do the bushing job. We discussed on the previous tape on making a verge, when we inserted the crutch wire in the wrong side, of how to remove the crutch wire from the strap verge, and how easy that was to do. These rivets can be removed with quite easy, and the bridge taken off for bushing that. We will not be bushing that hole. Let's try something here with this. Notice this. See how this wheel falls over due to the elongation of the hole. This is the classic job where a bushing is needed. I can't assemble that like that because the escape wheel must go in here first. Let's notice this. When I spin this on the back side, this wheel ceases to turn rather quickly. If I turn this upside down and do the same thing, look at the period of time that we spend now. Now that shows us the relative friction of the two positions when the pivot is in the worn section of the elongated hole. When I tore this movement down, I counted the train and did a little calculation here, and I have some numbers on this card. Let me find the right place. The ratio between the great wheel and the escape wheel is 2635.71. 2635.71. Whatever friction that we find on this pivot is multiplied 2,635 times as it is seen by the mainspring, in addition to the other frictional losses in the train. We find many of these old movements that will run with this type of wear, but we imagine the mainspring is weak, when in reality that's not the situation at all. Some other interesting things on this movement. I found that the great wheel turns one revolution in 24.23 hours. That says for 8 days we would need just a mite over 8 turns of winding on the mainspring. I found the escapement beat rate was 8,919 beats per hour, or 148.66 per minute. Now, when I calculated the pendulum length would be 6.26 inches. Looking at the pendulum and suspension spring and measuring from the upper end of the suspension spring, 6.26 inches comes to just about right here on the pendulum. Not to the center of the ball, but about here. And I said, I wonder about where that would be, the balance point of the pendulum. And if I should balance this on this screwdriver here, I am not too far not too far, possibly no more than 1/8 of an inch from the balance point. So this indicates that from a train we can find pendulum length. Those types of things help us if we have a missing pendulum rod or whatnot. But that's not the subject matter of what we're doing here today. Now, the next thing, before we do anything to the pivots, we will do well to take the ringing from the pivots that we have. There's ringing on this wheel, and one end of this one, and both ends of this one, and let's look at the escape wheel, and here, and ever so slightly here. So the thing that we should do first is to polish the pivots to see the sizes that we have to work the holes to. And we'll polish the pivots and then take care of the holes. Let's look at these punches here. That punch is 5/32 of an inch in diameter. 5/32 in round numbers is 156 thousandths of an inch. Has a hemispheric end, and in these tools, in this block, we go down to this one as the smallest one, and it is 60 thousandths of an inch, about 62 thousandths of an inch across its hemisphere. We will use those punches in a treatment of some of these holes. Now I know that hole closing, excuse me, I know that hole closing is a very debatable situation, and I know that the greatest butchery of clockmaking that I find is that of hole closing. But like most everything else that is debatable, the truth is somewhere in the middle of the road, not out on the extremes. There is a place for hole closing. And hole closing that is done in its appropriate place and circumstance is virtually undetectable in the end result and gives you a very fine repair. It is not a universal treatment for pivot problems any more than bushings are universal treatments for pivot problems. When I tore this movement down yesterday in preparing for this tape, I polished the pivots for the entirety of the strike side. And there was some ringing in those pivots, and the polishing removed. I measured before and after, and I removed from about a minimum of 1 or 2 thousandths of an inch to about 5 thousandths of an inch of material. Now in doing that, we go beyond the wear limits that we would like to have in the movement. The clearance would become too great, and in the strike side, every one of these pivot holes have been closed. I'm sorry, not every one. They were not closed in the great wheel, but 4 in each side of this plate have been closed. And I want to pull the camera in, and we will inspect that work. And I am certain that you will agree that that was appropriate in this situation. Let's talk about this hole right here. That is the hole that the fly pivot goes in. We have about approximately a 5-degree clearance here. 5-degree clearance being that we can slip the pivot in there and tip it about 5 degrees. We told you that these holes were as drilled here. We look at some of these holes here. We see what they look like. Incidentally, while we're here, this is the escape wheel pivot hole that we're talking about, elongated, that we will place the bushing in. You can see it's almost 2 diameters long. Let's get back to the pivot that was pivot hole that was closed. We're talking about this. I want to get this so that the light reflections are not obscuring the true picture here. Possibly right there. We're talking about this pivot, and at that point I would defy you to find any evidence that that hole has been closed. Let's move over to the next one. We're talking about this hole now. All right, let's move to this one. This one right here. Let's see if we can improve the focus a little. Right there. And this one. All right, those holes have all been closed, and I use the term hole closing as appropriate where that we need to pull in just a few thousandths of an inch, possibly no more than about 5 thousandths of an inch. Now, these holes on the front plate, this hole looked exactly like that before the closing. Right here. This one has been closed. And this one. Possibly about there. And this one. We're looking right here. Let's look at the inside of the plate. Here's the inside of the fly, the next wheel down the train. and the next one, and this one. So we see that there is a place where that even the most skilled workman would have trouble finding that it had been done. Let's find a hole that in the time side that has not been closed. Right here. That's the second wheel, not that one. This one is the second wheel in the train. We can see some scratches on this from previous assembly. Let's look at this one right here. That one has not. That is as it was made and as it is worn. This is one that we said that we would leave as it is. This is one that we said that we would place a bushing in, and that we would pull up, possibly tighten up on this one and this one. Now take a look at this carefully, and we'll inspect that same hole later after we use the closing. All right. Next, let us polish the pivots so that we know what to work to, and then we'll see what we can do about the holes in the plate. Back to the lathe setup. Let's look at the entirety of the lathe for a moment. The base pedestal, this is a V-bed lathe. This is a tip-over roller tool rest that we'll use in the pivot polishing. Here is the tip-over T-rest that we normally would use with the lathe. This has a lever feed tailstock, this being the feed lever, the locking ring. This is a collet holding tailstock. This is a collet holding the adapter for the pivot bed. The device that you can see in the background, and I noticed in looking at the pivot polishing, we can often see that's the locking lever for the tailstock. The headstock locking levers on the back side. This is the indexing feature on front. We drive from a counter shaft in the back that has pulleys of conjugate form to this, so that the belt tension remains constant on all of the positions. The belt is crossed here. The purpose of the crossing of the belt, this little bit of scrub right in this area reduces the resonant vibration of the belt at certain cutting feeds and speeds. The motor is a 1/15 horsepower direct current motor made by Bodine Electric Company. The pulleys here are conjugate in form, and the drive belts there, and the control box for the motor. This control box converts alternating current to direct current. It has a control that runs the motor on full field voltage all the time and has a variable voltage, not a variable resistance as a foot rheostat, but a variable voltage applied to the armature, which gives it essentially constant speed through a wide range of loads at whatever preset speed we have. We have the on-off switch on the control box here. That's the starting. This is the speed control, which we can carry down to very, very slow, all the way up to, this is full motor speed, and then we shift into a mode which is 2 times speed. And then we have the speed range again. So we have the variable range that goes through the 2 speeds. We have the reverse switch on the back. I noticed that when I reverse this, I get a little flick of noise on my TV monitor here. We have the escape wheel in the bed, and we will polish that pivot. And let's look again. We have the live dead center, live meaning that it rotates, the fact that it is machined, touched with the handheld graver, that we have a true female center in it, so it has the stability and accuracy of a dead center. We have the driving disc and the driving or the carrier that carries the wheel. If we take a look here, we can move this in and out for various reaches for different wheels. It's best to run this with the least amount of overhang in the event that you would get your finger against that. The pivot bed here. Let's drop on something for a background and see if this will improve our vision a little. I believe this blue possibly will do best. And we take the little pivot file, and we will run the file like this on the roller and against the shoulder, and we will take the ringing off of the pivot. Now I'll have to get down here with the eye loop to do this, and I may have my I'm almost certain to have my head in the camera, and I really won't be able to look in the monitor to see whether or not this can be seen. So let's see what we can do. Get the eye loop, get down here close. I have to do this left-handed. I am right-handed, but I have to do this left-handed to give this some camera space. Maybe I'll take that speed up a little higher and touch a droplet of oil on it. Now let's use a little burnisher on this. We discuss this burnisher just a bit. This is very soft, very flexible, very hard. Has a little plastic-like handle. When I say this is very soft, I mean it's flexible this way. This was issued to me as a workman in IBM over 40 years ago. If you would like to make a burnisher of this type, which is very good, use a piece of mainspring and work the edge to whatever the squareness of edge that you want, and pickle that in some acid for a few minutes. Those of you that are working in the jewelry trade have the pickling acid, and that gives this a very, very slight texture. Very hard, but very slight texture. Very fine burnisher. We'll run this speed up high and finish this off. And let's inspect it. And that pivot looks like glass. It is so highly polished. Well, let's do the next thing. Let's measure it. I don't have any evidence of it being cylindrical in the measurement. And the dimension on that is 57 thousandths of an inch. 57. The best I could tell in the study of this movement and studying and measuring all of the pivots when I tore it down and trying to measure places that did not show evidence of wear, the holes in the plates were around 61 or 62 thousandths of an inch. I presume they were drilled originally with a 1/16 inch drill bit, which is about 62 or 63 thousandths of an inch. And apparently the pivot diameters were set at about 59 or 60, so we're only a couple of thousandths of an inch down there. All right, we have the little driver. We latch that on here. We swap ends with the shaft, and we go back together again, and we're ready to polish the pivot on the opposite end. Now let's see how we come out on that. Let me inspect this and see if I got all the ringing out, and no, I did not. Just a little bit more. See the beauty of this setup. You can remove the pivot, take a look at it, go back in, and none of the accuracy or setup is lost. We wipe this pivot file regularly because we don't want the collection of the cuttings there. And we'll touch this just a little more. We're okay. Now let's put the burnisher to it. And we have to keep our finger out of the wheel. I'm pressing down on this burnisher rather hard, keeping it in constant motion because we don't want to wring this from the burnishing operation. And let's look again. And that is very, very good. Now, we'll measure this one and see what we come out with. Well, we are cylindrical, but we're approximately 1/1000th of an inch less than we were on the opposite side. So that is the job for that pivot. Now, let's pick up another wheel that we may have problems in and supporting, and look at that one. Let's take a look at this wheel. We have a longer arbor here, very short in that region. We go to hook up here. We can't reach, our carrier can't reach the window in the wheel. So again, we just slip on the little driver, and this arbor is shorter than the previous one. Remember that the other was the escape wheel. It has the escapement wheel out on the surface of the plate. So we have to shorten up in here, and I put that in backwards. Let's do it this way. I intended to polish the pivot on the pinion end first, and we set that there. We get our roller rest in position here, and we still cannot reach our driver out here, so we just move the disc out, and the crank pin may miss the may go over the top of the thumb screw, so we move the crank in a little, and there we are, ready to go. Let's lubricate the pivot a little. I want to see how bad the ringing is on this one before I begin, to get a judgment of how far to go. Okay, we go back in. I don't think that there is any setup that can be found in clockwork that is easier to get in and out of the lathe than this. This is a direct takeoff from the old English turns. We would be doing the same thing if we were using the English turns, except we would be powering with a bow. Now, let's polish this one. I'm holding down on the left edge of this file. The reason I'm holding on the left edge of the file is because the pivot is shorter than the breadth of the file, and I would be able to roll it over. So I want to hold on the left edge and back here so that my roller rest assures me that I get the cylindrical pivot. Let's see how much success we had. And we're okay. Let's put the burnisher to that one. And that's beautiful. Now let's go in the opposite end. We don't need the driver. We just slip the carrier pin right through the window of the wheel for this end. Let's see how much we have to take off. Okay, this end has very little need to clean up there. And let's move this back a little. I don't like the thought of getting my finger caught in the end of that pin, so I like to and not bring the pin through the wheel window any more than is necessary to drive it. Let's go again. I'm keeping the safe edge of this file right up against the shoulder, and from time to time I stone this file on the edge so that as it wears here that I maintain the sharp corner. We're okay there. Put the motor to the higher speed position. Let's take this up a little faster. I think we can make a little better time here. This is a very, very fine motor drive system. That motor is making about 3,500 RPM at that speed, and let's look at the pulleys. My countershaft is running about 80% of the motor, and it looks like the ratio here is about 80, so I must be running around 2,000 RPM on the spindle where the polishing is going on. So that one is finished. Let's really go through a couple of more of these. There's two more to go. Being that they have different locations on the arbor, different pinion considerations, so let's just belabor this thing a bit and see what we have to do. The pivots in this clock there are three sizes of pivots in the train wheels. The pivots of the great wheel are large. I didn't measure these, but then the second wheel is about 70 thousandths of an inch, and all the remaining wheels are about 60 thousandths of an inch. And that's the reason that I've been able to slip these wheels thus far into this one pivot bed. We didn't measure the size that we come out on this. That one is 58, and that one is 58. We didn't have to take off quite as much of that as we did of the escape wheel. Let's look again at how bad this one looks. This end of this one is going to require very, very little. The other end, a little more. So let's I believe that'll do that. Not quite. Let me tell you something. I was using a piece of paper towel here to wipe that off. I would advise no man to do that. Because that is much like polishing a watch case, a pocket watch case, with a chain on it. Those of you in the jewelry trade know the danger of that. That's the end of the chains, the end of the watch case, and it may be the end of you. You notice that when I did this, I folded this and got right out here. All I have to do for this to whip around there and tear this whole thing up is touch that pin. I really should not practice doing that. Let me look at this. That is okay. And we'll put the burnisher to it. Raise the speed. And that is fine. Let's see what we wound up with there. Well, that one is a little smaller. We didn't remove it in this trip, but that one measures 57 thousandths of an inch. And here we go again. We have to use the driver to make this setup. Incidentally, many clocks that have cut pinions here, we can simply fold this little crank arm right down into the pinion. Back this off if need be. Fold this little crank arm right down into the pinion and drive them right in the pinion. Of course, the lantern pinion, the shrouds obviate the ability to do that, and we have to have the driver. We might ask, what would I do if this pinion, if this pivot were so short that I could not get the driver on there? We ask the question, what would I do in that case? Well, over here in the pivot tools, we have a variety of these carriers that are straight with the tapered ends that will go into that. I would simply form a small right angle in one of these at the appropriate place and sit it down between the rungs of the pinion and just slip it right into the pinion. Okay. Turn this off. That's okay. I was afraid my roller might touch the wheel there if I just flipped it over. Possibly you can hear a little rumble in this. The pivot is chattering. The bed is slightly larger than the pivot itself, which is in its own right is okay, because as we file, we keep this caught up against the bottom and the rear of the bed, and I'm pulled up to zero clearance where the shoulder of the pivot is riding against the end of the bed. You notice if I touch it down with my fingernail, the sound goes away, and it runs smooth, and it will do the same thing when I put the file on it. So let's see what we have. See, the sound is gone now. More yet. More yet. I believe I have that. Let's look. It's okay. guys are 68 years old, you have a little problem lining this up, particularly when you have to keep your head back away from the camera there. Go on to the higher speed. I'm stretching this burnisher very tightly, pulling down on it. Pressure is quite great. We need to do this polishing job quickly, and the reason being, if there's any debris left in this bed, it may ring the new pivot. That's one of the reasons that I try to avoid using abrasive powders on burnishers, because the abrasive becomes embedded in the bed and is trouble thereafter. That measures 67, so that's just all right. We have one more wheel. This is the second wheel of the movement. The ringing is pretty bad on this end and also on this end. This one runs under greater force. Remember, I told you that we have two pivot sizes. This one is about 69 thousandths of an inch, and we will change to a new pivot bed, and that one is okay. There's some we have to move the crank outward. Straight pins are fine in here. However, they don't have the convenience of cranking them in and out as I do that. One of the other driving disc here has a variety of holes in it, so we can plug the pin into several places. But if I were using a straight pin on this and the hub was too big, you'd simply form the pin upward. But the crank is very, very convenient. We'll set the speed back down. We'll oil this first because we haven't had this bed in place, and here we go. Looking at this wheel, there's some wobble in that wheel, and there's also a little peripheral run out. But remember, we're running dead true on the pivots. Let's look. I have ever so slight radius at the shoulder. Let me be careful to get my file up close. I probably was not riding tight against the shoulder, and if you've studied tape number 18, I believe it is, that deals with pivot problems, you know of the problems described from shoulder radius. And where we put the burnisher to. Oh, that pivot looks like Looks like a piece of fine jewelry. We pulled off about a little less than 2/1000ths of an inch, about 1.5 thousandths of an inch on that, it looks like. What that really says, where we're pulling down 1 or 2 thousandths of an inch, if the pivots were not too badly worn and the holes are not too badly worn, we could pull off 1 or 2 thousandths of an inch in a polishing operation, go right back into the same holes. We'll discuss that pivot clearance a little more as we start working on the pivot holes. We have the other end in place, and I'm sorry that won't work because we can't drive it. Pick up a driver. Looks like the driver is on another wheel here. And we're okay. All right, let's see what happened then. I stuck my finger in the end of that wheel, and one of the things that we have with this crank drive pin is if we get strain on it, it will flip out and disengage. And that's the thing that happened there when I got my finger on the end of that wheel. Just got in a little bit too close. That was all right. See how we look. Okay. Okay. And 69 thousandths on that one. Let's ask the situation. Suppose we have a radius here that we just need to cut out, or suppose we have a shoulder that we need to trim up or whatnot. We would slip out this bed and drop in here a female center, and set this back up. We're on female center now, which is 0 clearance, much stronger, easier to work. You put on the tip over T-rest, pull it up into position like this, and take the handheld graver, and we would just machine that radius out. If we need to do any machine work on these things, it's best to do that prior to the polishing. But that's another facet of work that can be handled with the pivot polishing tools. All right, let's slip these pieces out, set them back to their appropriate place, and then we'll look into the plates. One of the things that I would counsel you on one of these sets, one of these pivot sets, there is, I think I said 3 or 4 dozen. I believe the count is actually 42 of these pivot beds that I have here in graduated sizes. They range from 25 thousandths of an inch which is about 0.6 of a millimeter to about 95 thousandths of an inch, which is just a scant 2.5 millimeters. And 42 of these, over that distance, the sizes are spaced very close to each other. If you get these out of place in this block that they're in, it would be almost disastrous to sort these things out in size order. And it's not as bad, but to some extent the same way with these little drivers here, because there are 12 of those, and they range from about 30 thousandths of an inch, I believe it's about 30 thousandths of an inch, to about 80 thousandths of an inch. So if you get those out of place in the block, you get bug-eyed trying to separate the big ones from the little ones. All right, let's set the lathe aside, and we will work on the plates and see what we can do with the holes in the plates. Let's look at our movement plates and think about something here. The biggest sin of rebushing movements is twofold. One is fitting the pivot too tightly. The other is not having the axis of the hole upright to the plate, called uprighting in old literature. Now let's see the things that affect uprighting. Watch this movement. Can you see me rack that plate just with my fingers like this? I am racking those pillows sidewise like this. See that? And this, and you see this and this. Now if we look at this situation, what do we do when we screw it up in the back frame of the case? You see, this thing is not rigid by any means. By no means is this rigid. We can twist it like this. We can rack it sidewise, whatnot. It says a movement of this class must have very liberal end play, end shake in the pivots, and it must have very liberal side shake in the pivots. That's the way it is. We find other classes of movements where the things that we'll be discussing here are not really applicable. Now let's talk about pivot clearance. Let's just drop this pivot in this hole and say, what is the clearance? I tip that sidewise like this. Now that looks like lots of pivot clearance. If I actually shake this thing side to side like this, I find that it appears lots differently. I must be tolerant of these strong mainsprings racking the movement and changing the uprightness of pivot holes. So I must have a considerable amount of this. And let's look at it. If we look right in the end, go round and round like this. About the best judgment position that I've been able to come to in one of these types of clocks is what I term as a degree of clearance. I'm not the originator of this term. I encountered it somewhere many years ago, where that we would say that a pivot has 10-degree clearance, 5-degree clearance, this type of things. And in every movement, as I place bushings or close holes or whatnot, or in any way deal with a pivot, I look at the plate and do this, go round and round and round, and I determine that I can tip this both sides of a right angle to the plate, both ways. And that assures me that my uprightness is not a problem in the movement. Now, you may consider this to be a very great amount of clearance, but I dropped that in a wrong hole then. But if you very carefully side shake this thing, not tip it over, you'll find that that is a relatively close fitted pivot there right now. Now, your judgment can be clouded very dramatically by the thickness of the plate. These pivots, all these that we're working on here this morning, are approximately what's called square bearings. And a square bearing doesn't mean a round pivot in a square hole. It's a term that's used in mechanical engineering. It simply implies that the diameter of the pivot is equal to the length of the bearing. That the diameter of the pivot is equal to the length of the bearing. These bearings are approximately square pivots, square bearings. If we look at this, that is 68 thousandths of an inch in diameter, and the plate is about 59 thousandths of an inch thick. If we look at this one is about 57 thousandths of an inch in diameter. The plate is about, what did we say, 55 thousandths, 58 thousandths thick. I don't know, there's a little burr on the edge here. But you see the pivot diameter is approximately equal to the plate thickness. Now, if this plate were twice as thick for a same amount of radial clearance, we would not be able to tip this nearly as much. Now, I have the wrong pivot in this hole here. This is the larger pivot. This is the hole for this wheel here. So let's see what this degree of clearance looks like. I laid out here trigonometrically a little chart that we can look at to get a judgment position. This is the center line here. This is the line of centers. This is 5 degrees, 10 degrees, 15 degrees. 5, 10, and 15 in the opposite direction. An old craftsman guiding me many years ago gave me some advice, and I found this advice in the American clocks to be very, very good. It is clocks of this class. In some others, this advice, this counsel is not really applicable. But he says 5 degrees is about a minimum. 5 to 10 is what you would desire, and he says if you've got 15, do something about it. So somewhere in an angle of tip about like this each way would be the thing that we would strive for. If I look at this, I don't know if I can get the perspective in the camera so we can see it, but if I do this, against this chart, I find that that wheel is tipping about the 10-degree limit there. I'm tipping about 10 degrees. If I shake this sidewise here, I'm not alarmed at the side shake, though it looks excessive from this standpoint. Now really I have the wrong pivot in the hole. This pivot goes in this hole. And that hole looks acceptably well right where it is. Let's try the opposite one, and likewise there. So let's say the material removed from these pivots leave these holes acceptably usable. Now we've got a problem though. We had ringing on the pivot. We've got ringing in the holes. We need to look into that ringing in those holes. So we'll pick up a tool and we'll do something about that. We should be able to handle that small degree of ringing with a round burnisher. Excuse me for reaching across here. We'll put a little oil on this burnisher. We'll go in this hole and give this some round and round here. Now we may possibly bring up a little burr or square up this entry end of the hole. We need to cope with that. Over here in our block we have some pivot swaging in our pivot tools. We have some pivot swaging punches. And we will do this. And I must get a hammer. That punch has an included angle of about 110 degrees. We go in that hole and we give that ever so slight tap and we inspect it. If that breaks the edge of the hole, we wipe it down with a burnisher, see how our pivot goes in it. That is infinitely easier than going in there with some chamfering reamer and breaking that edge. Let's do the same thing in the outside hole. And we inspect that and we go back again. Simple as that. Let's see what our clearance is and we say that's fine. Let's do the same thing for the hole over here. We burnish from two sides. And lost my punch. My punch rolled off under one of these pieces of colored paper that we have here. And I am breaking the entryway of that hole a degree that is just barely discernible. Just barely discernible. You might note that this never had an oil sink, still doesn't have an oil sink out there. And we'll say that finishes up setting that hole in order. Here is the next wheel up, and that goes in this hole. This one has more clearance there than we wanted, and we've got a little problem of this wire being in the way on this bench block. Try another bench block. Right there we have a place for this bench block. Now let's go into the hole closing situation. The ball on that punch is about the same size as the oil sink that we have. And we strike that about that much. And let's see what we have. Now that pivot will not go through that hole now. Pivot will not go through the hole. Let's go back into the hole with a broach. We want to close the hole more than is necessary, and then open it back up to be sure that we have a smooth and polished hole. Cutting broach, and let's try the size. And we must have been looking at a burr on that hole that prevented the entry, because we really didn't close enough. Let's try again. And a little more. And we'll broach that with a round broach. We'll touch the inside for a break. And we'll call that one okay. Now let's get the back side. Same one. That one needs even less. Okay. Too tight. And what do we have? Okay. Now let's inspect this hole closing situation before we get carried away with praise or condemnation. and knock off the tarnish here. I think I want to put just a little chamfer on the inside there. Okay. Find a magnifying glass. Talking about that one. Let's see if we can get within the camera where we can see this. If I can get the reflections in the Alright, we take a look at that hole. That one's been closed. Let's look up here at these two. See how they compare. The difference that we see is this now appears to have an oil sink around the hole. Now let's look at the size of that oil sink. Remember this pivot hole, the pivot that goes in there is 58 thousandths of an inch. The diameter of that oil sink, if you will, that we have left on the movement, the diameter of that is about 82 thousandths of an inch. So that says that that oil sink ring is less than 15 thousandths of an inch wide. This is flush with the surface. There's no scarring on the surface, either on this side or this side, and we have brought the clearance up where we want it. Now, if you should encounter this movement a year from now or a day from now in your shop, you would never recognize that that hole has been closed. Now, this is the case where that I maintain that there is a place for this type of work. We said this next pivot that we would do something to that hole. That one right there needs just a little. So let's do that. And we will do the same thing here. Still too tight. And we broach that. We're okay there. We said the other end was all right. This one appears as having an oil sink that's slightly larger than the previous one. Now let's deal with the bushing situation. Here's the bushing reamer that I use. It's 3 millimeters in diameter down here, and it can come from a tapered, up the taper, can carry that hole all the way up to 3 millimeters. I do this in the drill press. I lay the plate in the drill press, go in here directly, have a small drill press here, do that. So we'll put a bushing here, and we'll place a bushing here. This one seems to be okay in its location. This one is badly elongated. We need to do something about controlling that position of that bushing. And I need to pick up another tool. Here's a little tool that Mr. Coleman described to me some 30-ish plus years ago or more as being, he called it a preacher. Never seen that tool commercially. Little three-cornered piece, an unsymmetrical three-cornered piece of brass with 3 sharp-pointed center pins in it. One of them has a ring around it so I can identify it. And just to conserve time on the camera, I did this off camera. I located the marked end, to the best I could tell, at the original position of the pivot, and struck this with a hammer, just a light blow, and that gave us a tiny little dimple there, and let me find it right here in this plate. I can go back into this and drop those pins there and identify where center should be. I asked Mr. Coleman, I said, why is that called a preacher? And he said, I don't know. He says, an old clockmaker. And of course, Mr. Coleman was many years older than I, and I'm old now. But he said an old workman told him that that was called a preacher because it tells the truth of where that hole is located. Easy to make up. And when we get this bushing in place, I'm going to go back and check and see whether or not we really hit the spot. Now, the objective of this is that if we miss that spot, we would place a plug in the plate, mark it, and then drill in that plug. But an off-center bushing doesn't look real good. So I'm going off camera. I'll do this in a drill press. What I'm going to do is to set this set this up in the drill press in the position of the original hole. Go through this slowly and see if I can center this bushing on the original position. So we'll be back in a few minutes. Dealing with the bushing, we've drilled this plate right here and right here, and we take the 3-cornered scraper, the tip of that, we chamfer the hole ever so slightly on both sides to deburr it. We lay this onto the flat plate. We take the bushing. Now this bushing, the reamer can either be the commercial reamer. The reamer that I have is one that I handmade many years ago. I make the bushings on, when I make them up, this is a string of 15 or 20 or so. They can be made very quickly when you make a group of them. And we take this bushing, and I'm going to drive it in from the outside. This bushing has a slight taper on it, it's plate thickness, We set it down here and head it into the plate like that, and then we use a flat face punch to drive it in. I need to get the punch. Here we have the punch, and drive it in like that, and that is driven flush with the inner surface. We'll brush that off and be sure that we are down good tight on the inner surface. Brush this with a little wire brush. We're careful we don't have to have any punch marks or whatnot on it. And now let's slip the brooch in here. Be sure that our hole is deburred, and let me look at the tool of truth here, and I am okay. I'm okay there. Now, the thing we need to do here is to set the oil sink in this and ream it to size. Let's put the oil sink in first. The oil sink swaging tool, which we had here a little bit ago, right here. We can swage an oil sink in there easier than we can ream one. It also work hardens the bushing in so doing. Flat, hard surface here. We're still flush on the inside. Find our wheel that goes in there, which is this one, and we have to ream that, and the oil sink is too small for that pivot size. Let me go a little further. There we go. Now, let me test this brooch in another hole to see about where I need to go to. Okay, and we start reaming. I have to start with a smaller brooch. We're approaching the hole diameter. Well, not as close as I thought. Now, we're about, just about where we need to be. Just about where we need to be. We'll go in this with the burnisher. Let's deburr this a mite there. And let me swage the entry of that hole ever so slightly. Let's inspect it. And see what we have. And we're just about right there. Very good. Very, very good. Let's pause a moment. I'll look on this tape and see if we have time that we can look for a close-up inspection. Left on the tape. I'm J.M. Huckabee. Good to have you with us. This is the 23rd day of September, 1988. We will continue on the next tape, and we will inspect the hole on the next tape when we place the bushing in on the other end of the escape wheel. Thank you for being with me.